something else's. Okay, today we're going to continue on. This is part 2 of the MPI, message passing interface. So we started it last week, just introducing MPI as a library for sending communications. Went over the basics, the idea of sort of the main function calls that you have to make to start up your init, your finalize, what size and rank were, some of the utilities that you need to use to run MPI. There's sort of an ecosystem around it. You have to run it with a certain script. You have to compile it with a certain compile flags. Went through that. And we started on actually talking about how you'd want to use it, and that's the pairwise communication. The idea of it's a communication library, so unlike a pragma-based where it does the loops for you, you actually have to control sending messages and receiving messages. So you have you're running the same code on each processor. It can be anywhere between 1 and n. It can be across multiple nodes. It can be on the same node. And all you're really doing is controlling how those individual parts of the program are running, and any information you need. Say if it's embarrassingly parallel, you don't have to do anything. But if you want to send a piece of information that this guy needs to do this part of the domain, then you actually have to manually create a message and send it. And that's what we started the end of the last class. So we created our first message. This was just a hello world. Well, more than hello world, but basically a send and receive from rank 0. Rank being the who I am. That's who I. Rank is the ID of my processor. So if there's always 0 always exists. You always have to check for the other ones. So 0 exists. He can send a message, and then it will block and wait on rank 1 until it receives that message. And that's why we call it paired messaging. It actually has to match. So anytime you write a send, you're going to write a receive with it. Okay. So yeah, we sent that message. I just throw these in here extra just to review. We talked about this always having to have in the arguments, you have the message, the size of the message, the type of the argument in the message, and then the processor where it's going to go. And this one in here is the processor where it's going to receive, right? But you can also, MPI puts a little bit of programming niceness in this as well too, because say you had a loop and you were going n+1, and you always end up with 12 messages, and you've got 0 to 11, and you may want to loop back around. It has these other 2 flags called proc null, which basically means even if you create a message there, it actually won't do anything. It's just you'll see this. I put these in for more reference when you program. You'll see that this comes up in some of the examples because it's easier. Instead of having to put if statement, n-1, you can just say put that send message to, not go anywhere. So that's what the proc null does. And then any source means it's kind of like putting star or asterisk. It allows you to receive a message from anybody. So these are just more for making your life easier when you're programming. So if it's the last one in our list, you can kind of throw it away, or if it's in the first one, you can accept it. So these are just sort of built-in characters, so you don't always have to have the explicit processor. It's not too big of a deal, but you'll see this in some of the examples, so I wanted to stick that in. Okay, so now let's talk about, we're going to walk through this, and I want to go through this relatively quickly because I got a little behind last time. We're going to send our messages to the left. So we're going to try to build up some more complexity in our message passing. And this would be a typical type of problem where you've done some sort of domain decomposition, you've got a whole group of data, and usually in typical, PDE type problem, you usually only really care from your stencils about the data on the edges. The data in the middle is self-contained, right? What you care about is data on the edges. So you'll end up with this sort of type of pattern where, okay, processor 0 wants to send something to processor 1 wants to send something to processor 2. So this is this sort of pattern we're going to build up here, okay? So we've already created our send and receive where we did it between 0 and 1. Here, instead of just those if ranks, we're actually going to put a little bit of logic in there to say, okay, if I'm on processor 1, I'm going to go to n+1 and so on and so forth, right? So let's just walk through that. So let's just quickly review what we've got in our MPI code, C code here. We include the MPI library. We need to do our init, our com rank, com size. This is literally exactly the same as the previous ones, no changes. You're going to cut and paste this from every code you do, but it's still just a good review. Here, this is where we would do a little bit more logic, and this is where the idea of the proc nulls come in handy. So this is where it will drive you nuts a little bit, and where you're going to have to get out a piece of paper and figure out, your indexing. This is the manual part that a lot of people don't like about MPI, because you're going to have to figure out who's left, who's right, this type of thing. The actual message passing, let's just skip that for a second, is pretty straightforward. Send a message, same message from one. I'm just going to send one piece of data from here to our right. As I said, we're just going to send, and then we're going to receive from our left. So this is pretty straightforward, right? This is going to be the same. The tricky part is figuring out this logic of where these indexes are. Now this one's not too complicated. This is the idea of, left is rank minus 1, right? So I don't know if you guys can probably see that here, but let's go back to the other one. Okay. So our left and our right. So our rank minus 1. So we're going to go from 0. We're going to receive in 1. And if we're on 1, we're going to send to 2 and receive from 0. Okay. So that's easy enough. Left is rank minus 1, and then our right is rank plus 1. So that's pretty straightforward. And this is where it becomes a little easier if you use these proc nulls. If left is less than 0, if I'm the far guy on that side, then I'm not actually going to receive anything, right? And the same thing is on the far right. So this is just a way of, if I'm greater on the far side on this end, then I'm also not going to send it. So this allows me to use the same logic of the code here without actually having to put, I could just do left rank plus 1 and rank plus 0, but then I'd have to put special cases or if statements around the actual message passing for those end cases, right? Because those are the special ones. Everybody in the middle is sending and receiving. But the guy on the far right is only sending, and the guy on the far left is only receiving, right? So what I'm saying is this guy here and over here are our boundary conditions, effectively. And this guy only sends, and this guy only receives, right? So we have to kind of put in that. Sorry, you had a question? I guess technically it is, but I mean, how does it work out?
You manually.
Yeah, I'd have to check the header file how it's defined. May not be exactly an in. You could. I mean, this is pretty basic, but I think in this case it's probably the end. It's probably a negative integer. Or something like that to be valid. It's probably typed. You can look in the MPI.h and see what, and that might be, that dangerous thing about that is that might be implementation specific. It probably is actually in terms of to hit that tag. Anyway, but it's just a special flag so that you can cast it off. It just, as I said, just because of the examples here, it makes this programming a little easier. But, so this is pretty straightforward, even if we ignore those two, rank plus 1, then we can send. And so all we're doing is our messages, we're sending just our rank squared, and we're going to just cast our received back as just a negative number so we know what's going on, and then we can run that code. So in the examples there, it's called second messages. We compile it, and pretty straightforward. 0 sends nothing, and then it actually sent 0 but received nothing because it's on the far side over here. 1 sent 1, got 0, and then 2 got 1 and sent, it's the square, right? It's pretty straightforward. Okay? And then we can do this for a higher number as well. So this is just, all we're doing is sending one direction. So just left and right passing type of thing. Okay? So as I said, this is the same sort of sending, receiving, we're just not using the if statements. And this is sort of building up the idea of, in general, you don't want to have if processor 0, if processor 2. You want to make a code that will scale. And this logic here will scale from 0 to 100 or 2,000. It doesn't matter. And that's ideally what you want when you're doing MPI codes, is you want to avoid all these little special cases in them. You want to have something that'll work with 3, will work with 12. It shouldn't matter, because as you grow your program, you want something to work in parallel, not be specifically tied to a set number of processors. You want that to be a runtime thing. You don't want it to have to be coded in your code. Okay, so that's second message. Now let's add on something a little more complicated to try to complete the loop. So now we already have this code here, right? So all we need to do is put a little more logic so that instead of saying proc null, if we're at the end, we send that piece of information back to 0 to complete the loop. Okay? So it's emulate like a periodic BC type thing. So let's see how we would do that. Okay. So simple, straight thing we start out would be like, well, okay, all I do is take that piece of code, left still rank 1, I'm still rank +1, but if I'm less than 0, I'll set my left equal to size -1. Right? Simple enough. I'll just special case, instead of setting it to proc null, I'll just set it to the end value. And then the same thing on the right. I'll just set it to 0. Okay? Oops. So let's try to run those. So second message runs like we'd expect it to be, and as I said, you can do, 9 no problem. This is the case where it didn't have the periodic boundary conditions, so it's not sending anything. Well, let's try third message. It's not just slow, it's actually broken. So there's a case. What did we do wrong here? What did we add here? So why is this not? Well, I'm jumping ahead, but basically this creates what's called a deadlock. Okay? So this is the sort of classic parallel bug. And you're like, why? Everything looks perfectly fine. I'm looking at this code. Why is this not going to work properly? So this occurs any type of programmatically thing where you see a series of loops and there's no breakpoints. Whenever you see a closed cycle, like if you're in your programming loop type structure, this type of thing, you have a risk of this type of deadlock. Okay. Now, why is this happening in this parallel type of stuff? It was a key to something I just said a few minutes ago. Something about messages. Anybody have any ideas? Well, let me give you a hint. Remember when I said, let's walk through this code on processor 0. Okay? So processor 0 left equals rank minus, so in that case, it's going to be the second one. It's going to proc null, no problem. MPI send will send to proc null, then it'll move on to MPI receive, right? Well, what happens in the periodic case, that now that is going to wait for a message? That's going to say left equals rank +1, so it's going to wait for a message. Or it's going to send the message fine, but then this receive is going to wait until it gets the end receive, right? So and because these are paired messages, what's going to happen is it can't receive, it gets locked because it can't send, it'll send the message, but it can't receive this other message because it hasn't sent it. So it's this case of, there's the cycle, you need a start and a finish somewhere in that cycle, okay? Because these are paired messages. It can't move to this line unless it sends this one, and it can't complete that loop. So that's called a deadlock, and it just because your code will just hang. You attach a debugger, it'll just sit there waiting. It's like putting an if statement, if rank equals 2, and you never have rank 2, it'll just never go there, right? Okay? So the question is, how do we avoid this type of thing with MPI program? So this is just walks through it step by step, sort of if we laid it out. We send, that's fine. We send, but the problem is this guy's going to wait on receive, and this is sort of the chain of events that have to happen. Okay? And what happens is that it never actually gets to this. The send goes out, but then they can't receive this message from this neighbor because it hasn't got there yet, right? So, you know, all sends and receives must be paired at the time of sending. This is just getting you, for these block type messages, it just means that you have to make sure that your flow in your loop is such, or in your code is such that they can all get there and continue on in some sort of progression. And if you have any of these loops, you've got to make sure that you've put in a case or some sort of way that it will avoid that type of condition. Okay, so I'm just going to skip over the idea of buffering sends because I don't really have. I'll leave this for you guys to talk about later or to read through. It doesn't really matter too much. It's just the idea is there's different types of sends, as I mentioned in MPI. There's S sends, sends, I sends, and they refer to unblocking and buffering. And I don't really want to get into the details too much here because I don't have time to spend this. But it's just to be aware there are different types, and it has to do with whether it stages the information in a buffer or not. And for what we're doing here doesn't matter too much, but the different types of sends and different types of receives will matter depending on what type of program you're getting into. And if you take the summer MPI course, which is 2 days instead of 2 hours, we can get into that in a lot more detail. And I actually do have the slides here. We can talk about that later too. I just don't want to spend too much time on that one here. Basically, it's just saying, in this case, it's just buffering is dangerous. So that's why I'm using send to avoid buffering, because then you always know if it's not buffering, the computer isn't helping you. Anything you're going is going directly what you wanted. Usually the send is great because you may want to use it because now it'll buffer and help you those small messages. But when we're doing these programming examples, we want to avoid them because what happens with a buffer is you may be fine until you get to a bigger message now, and suddenly it doesn't work anymore. So it's not as safe as using the standard send, which is an on one. Okay, so without using the same MPI case or the same MPI that we've got, how can we go about sending and receiving and breaking this deadlock? So now a simple way to do this is why don't we just split it up? We'll do evens and odds because we have to take this loop and break it up. So we'll break it into 2 groups. So we're going to say all our evens, so our 0 and our 2 are going to send, and then we'll receive on 1 and 3, and then we'll just flip it over. So instead of doing one group of MPI calls in that nice loop, we'll just split it into 2, right? So it's not as efficient as just doing them all at the same time. However, we can guarantee that we always have starts and finishes. Okay? So the question is, so it's simple enough to do. We keep our top part the same as our other code that we had earlier. We just have to make these sort of a two-part wrapper. So it says we're just modding anything of the even ones. It's going to do this part first. And then anything that's on an odd is going to receive first. So see how we've just switched these? So we're guaranteeing that, okay, if I have 0 or 1, or 0 is going to send his message, then receive after. And then this guy's going to receive, then send his message, right? So this avoids that deadlocking condition, right? A little clunky. It's not idealized, but at least you can be sure that that'll work. So let's pull this one's in. So the fixed. So fourth. So here you can see where it's the same top, bottom, left size -1, size 0. Then what we do is we've just got this check here so that we only do the evens first, then we receive. And that's the fourth message. Okay, so and then that works fine, right? And now we have the case where 0 actually sends something and receives 9, right? So we actually, and then send, and it sees from left, and then we actually get something and send as well on the on the last one, right? So now with this even and odd thing, do you think it's going to work if I do an odd number of processors? How many votes for yes? It's not going to work? Lucky number 7. Looks like it works fine. Right? Like, what's the magic there, right? Well, if you think about the code, let's go back here. it'll still work because I've still got a broken. So what it's going to do is, say if I have 7, I'm going to get, 0, 2, and 4 are and 6 are all going to send messages, right? And then the other ones are just going to wait on receive. So I'm getting 4 messages sent out and only 3 received, but that's fine, because then when it goes to the next step, it's gonna now, I've broken that loop, so it's not as efficient. I'm going to receive on that odd one. They don't have to be exactly. They have to be paired, right? So that I'm going to receive. Still going to send and receive 7 messages. That's still going to happen. They're just not going to do it in the same pattern that I'm going to in this case. Okay. Yeah. Yeah, you could technically just break it in one spot. You could say only processor 0, you start sending and then start the chain. This is just a way of showing this, that ideally we're trying to do, as I said, we're trying to avoid those cases where I only put a special case in for those type of cases. This is just to show you and I'm going to show you a better way to do this anyway, but this is just sort of we're just trying to introduce all the little subtleties that can come from this. And to start, a lot of this, as I said, is thinking about how we're pairing messages and now that you're doing things, maybe not all in the same pattern, that's fine. You can have 0, 2, 4, 6 do things, and then 3, 5, 8, that's fine. And they can be out of order. It'll sort the messages out. It's just you have to make sure that there's a way that it can get all the way through each line of the code, right? And some are more efficient than others. Okay, I mean that's that when we're talking millions of messages. Yeah, this is probably not the best idea, but this is sort of just to get you thinking about how these messages interact with each other. Okay. Okay, so does at least that make sense? So we've introduced the idea of now we're sending left. We now can do like a periodic boundary partition type problem. We know how to avoid deadlocks using a send and receive. Okay, the most basic of MPI routines. Now, as I said, I'm going to tell you a better way to do this, and that's like the MPI guys aren't dumb. They know that this is very common, that I'm always going to have an MPI send and a receive bolted together, or one after each other. So they're like, well, if I'm always doing this, why am I putting 2 functions every time? Why don't I just make 1 function? Wouldn't it make more sense if I could actually just instead of making 2 separate send and receive, why don't I make a send receive? It's just 1 function, so that I can send and receive, pieces of data, because I'm usually sending and receiving each time because I've got those proc nulls and that type of thing to handle that. So that's exactly what they did. They created a send receive, which is literally just those 2 functions jammed together. It's still a blocking message passing. This one won't go past until the send and receive is done, but it's done in 1 function. And the nice thing about that is we never have to worry about a deadlock, because inside this function, it's going to sort out that issue about one going first or who's going to next. It's going to do that automatically for you, because I don't have to go send receive and then receive send. It'll sort all that out inside. I just make 1 function call. Now it's a little longer, because if you can see the green, I've got my send message, and then I've gotten the purple at the bottom, that's my received message. Same piece of information. If you look back in our other syntax, it's just they're all just jammed together into 1 function call, right? So this is blocking. It'll wait until both are sent and received, but allows them to happen simultaneously. So in that 1 function, I can actually just go send receive. I don't actually have to have those 4 lines of the other code. So it's simpler from a programming point of view. And it will automatically pair these sends and receives inside. You don't have to think about that step yourself. Now there's reasons you may want to control it yourself, but if you're just doing this type of data where you're just, okay, I'm always receiving something from my neighbor and sending something to the other side, which is usually some sort of regularized pattern, then this is going to make your life easier, and you're going to have less screw-ups and this sort of type of thing. People do ask sometimes, why are there 2 sets of tags, types, and counts? If it's a send receive, aren't they going to be the same counts and the same types? Well, normally that's how you're going to do it if I'm sending the same piece of data. But there's nothing that stops you from using a send receive to receive 1 type of message and send another type of message. They don't have to be matched. So that's why most of the time, these 2 here are going to be the same. You're going to want to tag them differently, but the counts and MPI types, usually you're receiving in 10 doubles, sending 10 doubles, but in the general sense, they don't have to be exactly the same. So let's look at an example of how you do that. So we literally can replace those 4 lines of MPI from the previous code with a send, receive, and then receive, send. And then we can just replace it with one function call. And we don't have to worry about the deadlock. So we just make one function call. So we send our single double, right, to the right, and then we receive from the left, okay? And we don't have to worry about the proc null. We can do the periodic boundary condition in this case because it'll take care of the pairing and not worrying about the deadlock type thing. Okay, so let's this. So for that, in this case, that's 5th message. So we've still got our periodic boundary conditions set up, but it's much simpler. That's the whole code right there, right? Now we can replace all that special if statement stuff with just this one guy, right? And as I said, the key to MPI is use the least amount of MPI calls you can get away with. Much less problems, you're going to screw something up, and usually it's more efficient. That means less messages is better. So instead of 4 calls doing something, yeah, this is still under the hood 2 messages, but it's going to still do a better job if you can just get away with using this. Okay? Yeah, it's a little longer in the syntax, but I think it still makes more sense because now you're going to think about it. Okay, I'm always sending, receiving. You're always going to program it in a way. So here's my message going out. Here's my message coming in. Okay. So, sorry. This one here. Okay. So let's go to. We look at 5th, and not surprising, it works exactly the same as the other one, because they are doing under the hood. It's doing that. It's just doing that for you. You don't have to do it yourself. So within the library, and that's what a lot of MPI is under the hood. There's really only a few things going on, but they've put a bunch of these features together to try to make your life easier, because these are the most common sort of message formats you're going to use. Okay. So as usual with examples, at the end of this, you're going to ignore all what I've just told you before that and just use this one. And for most of the cases, that's probably all you're going to want to get away with. Unless, once again, if you're doing a different communication type of approach. Okay? Yeah, so 5th message works. Nothing special about that. It's just another way of doing it. But I think it's cleaner from when you look at it and cleaner when you think about it to use that. Okay, so that basically that's the very, very quick and not thorough enough summary of paired message sending receiving. That's sort of the key component of MPI. There's lots more to it, but that's one of the key components. You send and create messages. From just that, you can create a parallel code, send information back and forth. Every processor is going to run it, and you're going to organize it. And that can do most of what you wanted to do. Now, if you remember when I talked about MPI in the previous class, I said there was 3 main functions it did. One was paired and was message passing. One was collective operations, and the other one was memory operations. So we've covered sort of that initial idea of the original paired messages, but now we're going to talk about collective operations. And collective operations really are just a collection of higher organized function calls that allow you to do message passing, but you don't have to generate all the sends and receives if you're doing certain types of structured message passing. So say you wanted to do a global sum between n processors. You could write that using the send and receive, no problem. I collected all the processors 0, I build a tree graph, I do something. Well, it would be better if we use the built-in MPI libraries to do that. And luckily MPI they've already written those for you, sort of the normalized type thing. It's kind of like, you could write your own square root function, but who would want to, right? You want to use the built-in ones. This is the same idea. So for type of operations, like you want to calculate the min, mean, max of some random numerators, how would you MPI this? As I said, you could write your own. Here's just a simple example. We're going to have some data at the top, init, com size, com rank. I could easily just, everybody generate some random seed number. Everybody find their own components. Just loop through finding the min, mean, max of the individual piece of data that I have. Pretty straightforward. This would be no different than any serial code. It's just you're only doing it on the piece of numbers that you have. But then I got to do this ugly MPI stuff where I got to go, okay, I got to send a piece of data, and I have to check, is it the biggest one, is it the smallest one? And I have to go through all this logic here and track, okay, receive this one, if it's not the 0. So in this case, I'm saying everybody who's not 0, send a piece of data, and I'm going to be processor 0, going to be collecting all the information from all of my processors, and then we're going to sort this out. And then I'm going to output the data at the end, right? Now I can do that, and it's perfectly valid, but it's pretty clunky, right? And this is pretty inefficient too, because now I'm getting this sort of what we call a bottleneck. Is processor 0, you got 10 processors, that's fine. But if you start doing 100,000, processor 0 is going to be overloaded, just collecting piles and piles of messages. Ideally, in a parallel code, you want them as load balancers as well. That's for the workload as well as the number of messages. So even though the workload's pretty cheap, he's receiving thousands of messages. From the guy sending one, that's fine, but that's thousands of messages, and that's just, if you looked at how much time is being spent, it's just going to be spent receiving messages all the time. So ideally, this is not the best algorithm to use. Better would be to do some sort of tree-based, scheme where we reduce as we go along. But we could program that ourselves, or we can just skip it and say, why don't we know the guys who wrote the MPI library know way more about communications and the underlying functions. Why don't we just use their function calls? So they have a whole bunch of these collective routines, and they usually have this sort of moniker with all in the front of them. So MPI_all. That's sort of a key to tell you, okay, anybody in a certain communicator is going to be involved in this. Okay, so that's important when we program our code. You can't bury part of this if rank equals 0 and then put an MPI collective in that function, because it'll never work, because it expects everybody to be part of it. Okay, so it works similar to our send and receives in the sense that we have a send and a receive pointer, because we're going to do all reduction. We're going to send a piece of data. We're also then going to receive a piece of data. We're going to have a count, just the same size of amount of data that we're working on. It could be a whole array. A type, an operation, this is the one that's a little different, and a communicator. And so that operation is what type of operation we want to do. So this is all standard to our regular sends and receives, but this is a new one. It's either going to be a sum, a product, a min, a max, any type of thing you could do in a collective type of operation. And it's going to do this way more efficiently. And even in modern systems, it actually does this in hardware. So it actually doesn't even do it on the processor. So on high-end HPC networks now, a lot of this type of operations, the library offloads this out into the network itself. So as you scale up to really large numbers, you can avoid a lot of these reduction operations taking overhead, right? You don't have to worry about that from the sort of your programming model, but it's even more reason to use these function calls as opposed to writing it yourself, okay? And to say, back to your communicator, if you really only wanted to work on a subset, you can still use these collective operations, but you just have to create your own communicator that is that subset. Otherwise, every time you go MPI all reduce for MPI world, it's going to try to involve everybody and all of the processors. So that's a case where you may want to create a communicator that's only going to work on its half the data or something, because that way you can control that way. Yeah.
Trying to get players to set of 8 nodes.
Yeah, so there is, we're not really going to cover here, but there is, you can give topographical constraints for the network you're on. You can tell it's a mesh or a grid, and there are ways. There's something called yeah. The short answer is yes. You can make it aware so that locality matters. Yeah. Anyway, so yeah, so that's the basic of a collective operation. So in this case, you want to do your min, max, reduce. It's pretty straightforward. We can make 3 calls just to our, we do our data set exactly the same, but instead of having to have all that sort and collect to processor 0, we can just replace that with a bunch of reduction calls for min, max, and sum. So you can just see a min, max, and sum. It does those 3. We get our global data. The nice thing about this one is it doesn't just all collect it to 0 and then we have to send it out. it actually collects everything. It actually does the calculation and sends it all back out to every processor. So say you're doing something like an L2 norm calculation where you need to scale everything. You don't actually have to go collect it all to one and then send it back out. It'll do this at the same time, which is why everybody has their local data and then a receive as well. So it's going to collect it all and broadcast it all back out at the same time. So it's sort of doing two things at once. So, it's giving you back everything. Even if you don't need it, maybe you only want to output it, but it'll do this within the same routine. So, as opposed to parallelized messages, all processors in the communicator must participate. So these are blocking globally. In the other ones, we would block, each individual thread. This one, it basically, you go through all the tasks running on every processor until they all get to that all reduce operation. It's going to wait there. So this is why it's a little bit, you want to avoid it unless you have to, or you want to put it in a part of the code where they're all going to get to, because if one part is much faster than the other ones, it's going to block everybody at that point because it can't continue farther in that code until it gets a piece of information from everybody. Okay? So just be aware it can be a more expensive operation because as you scale, you're going to get more and more pieces of information involved. The other one, they may only block the local processor until he gets his pieces of data. That's not as bad because at least you're not holding up other people. But these collective operations, that's fine. You may have to do that, but it's just you have to be aware that you could, if you've got one with twice as much data, and there's 10 processors, all other 9 are just sitting there waiting at this all reduced doing nothing, while this other guy. So that's why load balancing is really important. I.e., everybody has as close as possible to the same amount of work. Okay, so that's sort of the general overview of the MPI parts. That you're going to have to go back through this stuff and look at the source code. That's what those examples are, to kind of wrap your head around what was going on there and run those cases and play with them. But with the parallelized communication and the collective operations, that's usually enough to do most of what you want to do in a typical scientific programming code. So what we're going to talk about now is the normal type of things. You'll see where I'm going to go with some of those examples. What you normally would see in typical type of science codes, where you have, you've got serial algorithms that you've decomposed different ways. You've got time marching schemes. You've got different stencils. You need global norms. You need to apply boundary conditions. These are sort of the real things that you do in your serial codes, say your wave equation you're solving with a finite difference there. How do we apply, or how do we best do those in parallel? And what communications do we need to apply with that? Okay? So, normal we have this typical finite difference stencil here where we just have this, this pattern like it's just 1D where we've got this, stencil where we need our left and right neighbor. We're doing our spatial discretization. In serial, we just start from 1 and we just step through to n plus 1, no problem, right? In parallel, but this could be bigger too if it's a higher order stencil. But we always need they're relatively local in the sense that for this calculation, I only need 2 pieces of data, right? But I got to make sure I have that neighboring data, which is easy when I'm either in if I'm sharing all the same memory. But in the case with MPI or distributed memory calculation, I may only have part of that domain, and that's where the message passing comes into it. I get to the end of current domain and I need a piece of data from the other guy. That's when I need to put my message passing in to finish that up, okay? So this is a diffusion equation example, but it doesn't really matter which one. The idea being is you're taking that 3 pieces of data, you're going to time evolve it to the next step. I can do all of these at the same time, but I can't move them forward until I have all of that information for my next step. So a common way to do this, and it's fairly efficient, is to add guard cells or halo cells or whatever you want to call them, basically an extra fake cell on the end of your domain, and we're going to use that for multiple purposes. One, we can apply boundary conditions there. That's the way it works well. But also well, as we break this up into multiple pieces, we can use that as our buffer to save information. So as I'm taking information from another processor, I can stick it right there. So this is always the view I'm going to see. This is the global domain, but as I break this up in parallel, I'm going to have that as a local domain as well. So if it's a real AND like processor 0, and it's just a fixed boundary condition, then I'm just going to hold that data there, right? But if it's an internal boundary or artificial from doing things in parallel, that's where I'm going to copy my message, my information into, right? So it's pretty straightforward. All you do is you just literally go add 2 to your normal domain that you would regularly have. So domain decomposition really is a fancy word for just means splitting up what you've got. In 1D, it's really easy. I have 1,000 cells. I have 10 processors. Everybody gets 10. In 2D, I've got 100 by 100. I want to divide them by 4. Everybody's got 50 by 50, whatever, right? 3D. Now, there's a lot more complicated ways to do this. If you're doing unstructured grids, it's even more complicated because where do I put my boundaries? Structured ones aren't too common. You can do adaptive mesh refinement. There's a lot more fancy ways, but at least the basic idea is the same. You want to break this up into pieces that correspond to the physical domain that you have, and you want to work, like you said before, locally. You want as much, you don't want to take a piece here, 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 and here. You ideally would have, most of your local data as close as possible, and the amount of area that you have to message pass as small as possible as well. Because we look at our stencils, we know this guy here is going to work on these 4 pieces of data. So if it's spread all over the place, all you're going to do is spend all your time message passing. So really, and there are very good algorithms, Metis, Scotch, these other tools that will do this for you. If you have a regular data set. If you have structured data, this is pretty easy. You just literally go, like I talked about before, you just 50 by 50, you just divide it in half or whatever, right? So this is a case here where we use that Go cell domain, so we're going to split this in 2. So we have a global domain, and we need to split it in 2 pieces, okay? Well, what we do is we just take the first, say we have 8 cells that we want to do up. We put 4 and 4. Straightforward enough. We're going to pad that extra Go cell, or we're going to add an extra piece or guard cell on the end. And we're going to use that as our buffer or our communication. So from each processor, he only sees this local number of cells at the top there, and then processor 2 sees this one over here. And our communication, or our MPI, is going to happen at that very end, intermediary point, right? So processor 1 has to send a piece of data, and it's going to just send it into this buffer here as a storage location. Then processor 2 is going to send his 0 back to the other guy. So unlike in our previous example where we're only sending left, here we're going to send left and send right, effectively, right? We're going to send, receive the same piece of information back and forth. And you can kind of see how this works. That will be very similar regardless of how many of these pieces I break that up into, right? The idea being is as I loop through this, that piece here looks exactly the same as what my serial code looked like, except for the fact that I have to wait for my message to update that piece of data. But the rest of my code doesn't even know the difference. So really, my message pass update is really like just filling in a boundary condition, right? I'm just updating it from somebody else's information, right? It's an artificial boundary that we're imposing to do this in parallel. However, the structure of my stencil, my time stepping scheme doesn't change. I just have to synchronize it in the same pattern. So if you're doing this type of explicit type scheme where you only have local data, you can get away with this relatively easy, right? At least in 1D. Now in 2D, this becomes bigger because now you have a whole interface. And in 3D, you have a whole face. So it gets more expensive. But you still can do it. It's more bookkeeping, right? So at least from a conceptual point of view, you kind of see how we can go from just a series of message passing tools to just apply them to like a stencil type program, right? Yeah, there's details here, right? Of course there is, right? But it's not, the breaking it up into different pieces is relatively straightforward using this methodology. And as I said, you don't have to modify as much code as you think. Because if we go back to just, I'm only guy working on this processor, if I just take this as I already have this piece of data, that's exactly the same as what I'm doing in serial. Instead of just going from 1 to 1,000 on the processor, I'm now going from 1 to 100. And the other guy's going from 101 to 201, right? So now we're doing 1/10 as much work, i.e. so we should be faster. But we have the overhead of when we're done that first 100, we now have to wait and do a message pass to send that one piece of data at the end. So all the code, all the MPI calls, I said at the beginning, there's hundreds of them, but you really can do all of that whole scientific code with just this few commands. Init, finalize, we need those. I don't think I have it on there. Maybe I don't. The column size and rank. Now we can use send and receive separately or just send and receive, right? So we actually don't even need those two. We can just get away with this guy. And then we can do, if I'm taking a norm at the end, we can do an all reduce, right? So just with those few commands, I can do a whole find a difference code without any more MPI required. Yeah, there's some bookkeeping. I got to figure out my lefts, my neighbors, my lefts, tops, rights, or whatever. In 1D, it's not too bad. It's this guy, it's that guy. In 3D, now you have lots of neighbors. But it's the same thing. You're just striping in different patterns, right? And the trick of this is it's relatively easy to do it and get it to work well. When you scale this out to a large number, in 1D it's no problem, right? But in 2D and 3D, to do this efficiently so that communication just doesn't dominate everything what you're doing, that can be a bit of a balancing act. Okay, so in the code we've got there's the examples there to go through, and that's most of what I have to go through. I can touch on a few other little things. This is everything you need to do the assignment. The assignment is just going to be basically redo the assignment that Ramsey's already had. You did it with threads. You're just going to redo it, same code, just doing with MPI. And so if you you're going to have to go back and step through this and work this out. But basically, most of the MPI you need, you can copy from those examples, right? It's just you're going to have to reorganize where it's going to go. And as I said, instead of sending left, you're going to send left and right? You got to send a data to both pieces. You will have to scratch your head. It takes a while, a little bit, to get your head wrapped around it. But that's the process of the MPI. The MPI part is easy. Sending message is not hard. This is the easy part. It's actually thinking about how your code is going to run in parallel and how you divide it up and do the work. Because you're taking something that was inherently a serial code and trying to, break it up into a way that it wasn't originally designed for, but also so that it work in parallel and remove as much data dependencies as possible inside it. Right? Luckily for the 1D case, that's pretty straightforward because your only data dependency is within a time step, just that one piece of data on the end. Right? I've got more slides in here too. I can go through them quickly just to talk about other types of features of MPI. Not enough detail, but this is just an example. If we go back to the very first, we talked about MPI, or when we talked about tools, there are lots of tools, some better than others for parallel programming, that show you what's going on because it gets hard to visualize. Here's an example with a trace analyzer from Intel showing you I've got 12 processes running, and it's showing the blue means that's the code doing something. Red is actually waiting for an MPI, and here you can see send, receive, as it waits and breaks this loop. And here's a case where you're spending a lot of time, and this is because, as I said, this is a global collective operation. So all of these guys, even though this guy's done fast, he has to wait until this guy gets done so that they can all do their operation together. And this is just a visual reminder of, okay, these are expensive operations because it doesn't matter how fast these or how slow these guys are. These are fast, these are slow. There's always going to be a limiting step of them if using that reduction operator. So it's just whereas these guys can go, as long as this one has a piece of information, he can jump ahead, right? So it's just illustrating a point that you have to be careful. Use MPI as little as possible. Or if you program your code and you're like, why does it seem so slow? You may want to use one of these tools, just like profiling, just like debugging. There's a parallel debugger too. Linear DDT will actually allow you to track each individual thread as well and do some of this bookkeeping, so you can see how much time you're spending in MPI. And if it's more than a certain amount of percentage, you're probably wasting time because ideally, especially at low numbers, you want enough work in this section here that this is relatively small, right? Now, I don't have time to get into it. But everything we talked about today was blocking communication. That was pairwise, where it says, I send a message and then I wait till I receive it. Now, one of the most efficient ways that real codes get away with that is they say, well, that's wasteful. Why am I waiting around not doing any productive work while a message is being sent and I'm waiting for it? I could go off and do something else and then come back and wait for that message. So that's called non-blocking communication, where you actually decouple the send and receive. So send goes through, then you go off and you do some work where it doesn't rely on that piece of data. You get that processor doing something else. And then you come back and test, do I have that message yet? And then go on. But as you can imagine, that's going to involve you. Block message is safe in the sense that you always have this very regularized pattern, right? This can be more productive, but now you have to do extra bookkeeping. You got to know when to recheck the messages. You got to make sure you don't overwrite memory, this type of stuff, right? But it automatically avoids deadlocks, right? And it can avoid system buffering, and it's a mechanism for overlapping and interleaving communication. Because ideally, instead of waiting around in here, this guy could go off and fork a little bit and do some other work, calculate something else, and then come back and get that piece of information, right? As you can see where that could become an issue as you go to larger and larger codes, right? So inherently, when you're doing your initial MPI codes, you're usually going to start with a send receive. And if that works and you're not having a performance head, stick with it. But as you grow the size of the program or the number of communications you're going to go to, and you profile it, and you're like, oh man, I'm waiting a lot of time, you may actually have to, take that send receive and then break it up into a non-blocking type communicator. But it'll be that sort of stepping procedure, right? I've got some more information in here about the details. I don't think I really have time. It's already 12:04 to go through all this type of stuff. But I left them all in the slides just there for reference. And then I put some more information on other types of collectors, broadcast, scatter. These are just ways of sending data. This is good just reference information that you should just read through, and then broadcast and stuff as well too. Okay. So we don't really have a lot of time in this course to cover in depth all this type of stuff. We're just trying to give you the general flavor of it. In the summer school that we have, we do spend almost at least a day and a half with a lot more advanced. We actually even get into some of the topologies and stuff. So if that's something you're going to be spending more time with, then it might be worth your effort to come back and just do that particular sections of it, because we can do it more in depth with more exercises, hands-on, that sort of thing, which is the best way to learn this type of stuff. But I think there's enough of a flavor here just in those first to do that basic example, so you get the idea of what MPI does and what's included into it. It's not exhaustive for this, what we're going to cover here, but at least it gives you the idea, if you're using an MPI code, what's going on behind the scenes. Okay.